basically completely new topic. So the topic is affine algebraic variety and algebra of commutative rings. So today and on Thursday, I will talk mostly on this topic. So let me not completely informally say there is something called an affine algebraic variety. So affine algebraic variety called X. I'll say what it is in the course of a while. And there's something called I can go from this X to something called K of X. So this is going to be its coordinate ring. So, you know, if you want, this is polynomial functions on X. On the other hand, I can start off from more or less any ring A, and I can go back to something called spec A. So this is, in good cases, this is an affine algebraic variety, or more generally it's an affine scheme. And, you know, if under good circumstances, under good conditions, then X and A are more or less the same thing. So more or less the same thing. So of course more or less is not a very strict mathematical statement. I hope I'm going to be able to get a little bit more precise than this. So just to set this in context, earlier in the course I was talking about varieties. So for example, a conic in A2 or P2, or you know, this I had these PNs and so on. So these are the previous varieties. The varieties in the previous lectures can basically be understood as sets only. So whereas to say what this algebraic variety X is, you know, it's much more than a set. It's got much more structure. And we basically can't make any more progress. All of these were geometric locuses. So, for example, I talked about the Grassmannian variety. I talked about how to embed it in projective space. And the secret to that was I can somehow find a formula to display all the points of the variety. So, sort of basically explicit. And, you know, this doesn't work in more complicated cases. So more complicated cases need more theory. So I'm going to start developing this, this theory, and the theory is this thing called the algebra of commutative rings. So commutative algebra. So today's lectures and Thursday's lectures are basically concerned with algebra. So they're concerned with algebra. And the typical ring is K of x1 up to xn, divided by an ideal. So later on we'll see that this ring K of X, under the good conditions that I intend to impose, this is exactly of this kind. And then, so studying the ring here, once we've chosen its generators, we get out this ideal, which is all the relations that hold between the generators. And knowing this I is more or less knowing the same thing as X. So, you know, that's how we go backwards and forwards between an algebraic variety, a geometric object here, and this algebra. But anyway, let me start simply. So you know, I should say some definitions. So a ring A. So I want it to be commutative and with a 1. So if anybody needs me to repeat the definition of a ring, then I can do that. I can do it, but it's just basically a waste of time. I mean, I'm sure that you've all seen there's a plus operation there. I can add elements of A, and there's a multiplication operation. The plus is a group. The multiplication is, you know, has this distributivity law. Let me just assume you know what a ring is. Right, I insist it's commutative, so when I do multiplication, xy equals yx, and with a 1. So there's this element 1a. Right, and so homomorphism, you know, 5 from A to B. You know, this is, the ring has these two structures, plus and multiplies, and my ring, my homomorphism is required to satisfy this. So A plus or minus B is phi of A plus or minus phi of B, and phi of AB is equal to phi of A, phi of B. And I'm dealing always with rings with a 1, so I always insist that phi of 1a is 1b. Okay, so I mean, if you're talking about algebra, you have to give the definitions at the beginning, but I'm assuming that everybody here has seen this kind of construction. Right, so the option, these are not conditions that we need at once, but usually we don't get very far without assuming a bit more. So optional A contains a field. Right, so my ring A contains this element 1A. And so it contains, you know, 1 plus 1 plus 1 plus 1, and it also contains minus of this one. So it contains, so either contains Z mod n for some n equals a characteristic. So this is just the first time when this number is 0, or it's 0 if, usually, and so sometimes it can happen that, does it contain n over m? So if so, if the characteristic is 0, and A contains all of these expressions n over m, if so, then Q is in A, and it satisfies it. So the rings, the typical rings, as I said, the typical rings in algebraic geometry are, you start with a field, and you add this x1 up to xn, polynomial generators, and then you divide out by the ideal I, and so this automatically contains K. This automatically contains a copy of K. So, for example, Z does not contain any field. So sometimes, this is a condition which sometimes I'm going to impose, and sometimes going to come for free, but it's not always satisfied. So optional, again, another optional condition. A is an integral domain. So, for example, if I do k of x, y, and then I divide out by x, y equals 0, right, then, this is the functions on polynomial functions on the union of two coordinate axes. Right, and so this contains the function x, which is 0 there and not identically 0 there, and it contains the function y, which is 0 there. Sorry, the function x is 0 on this axis and not 0 on the other axis, not identically 0 on the other axis. Y is the function y is 0 there and not 0 there. The product xy is 0. So here x is not 0 and y is not 0, but product xy equals 0 in A. Right, so this can happen in perfectly simple situations which are closely related to algebraic geometry. So sometimes this happens and sometimes it doesn't. Right, if you do I'm sure everybody knows that if I do z modulo 6, that this is z modulo 2 product with z modulo 3. This is as rings. And then, these are not, this is of course not an integral domain, because it's the element 0, 1 times the element 1, 0 is 0. Okay, so that's so much for the definitions. So integral domain, I should say what the definition is here. Integral domain means, so by definition, this means that 0 is not equal to 1. Right, there are some rings, well, there's exactly one ring in which 0 is equal to 1, so it's the 0 ring, and no 0 divisors. Right, so if a product xy is 0, then either x was 0 or y is 0. That's integral domain. Okay, so the having said what a ring is, I want to say what an ideal is. I in A. So I hope that this is already familiar to everybody. Subset I in A is an ideal if, so I want to say it's an additive subgroup under plus. So if I take two elements in here, if I take A, B, if A, B are in A, sorry, let me say I, J. If I, J are in I, then I plus or minus j is in I. Right, so this is one condition. And the second condition, I want this to be closed under multiplication by elements of I. So I want that for all I or for all I in I and A in A, the product A times I is in I. Right, so I hope everybody has seen this and this is not causing any difficulty. So what do I want to do? Why do I want this? So so as you all know, in Z, every ideal is either 0 only or is n principal ideal. Z times n, so the set of all multiples of n in Z. So you know this guy here is not a subring of Z, because I said that rings, all my rings are commutative with a 1. So if x, except for this trivial case n is 1, this is not a subring, but it is an ideal. And so, and divisibility in n in Z is the same thing as inclusion of ideals. Right, so you know, I can say that n divides m is the same thing as you know, the ideal of all multiples of n contains, so this is n divides m. So in other rings, you know, if I have some you know, more general ring, then this statement, divisibility makes perfectly good sense and ideals make perfectly good sense, but this statement is just not true. Right? So this is one of these kind of issues in commutative algebra. You see it already, you know, in absolutely elementary, in primary school mathematics, that we want to say that you know, we want to study divisibility properties. In particular, I'll say in a minute, we want to study unique factorization. And, you know, it's there are the cases, the motivational cases, the cases we first studied, Z or the polynomial ring, which I've already discussed. And you get statements which sort of suggest things in more complicated cases, and sometimes they're not true. Okay. So I hope everybody knows if phi from A to B is a homomorphism, then kernel of A, so this is a set of kernel of phi. This is a set of elements A in A such that phi of A is 0. This is an ideal. Right, it's an ideal because phi is a homomorphism. So if two guys A and B, if two guys A and B both map to 0, then A plus or minus B maps to 0. And if either A or B, if B maps to 0, then for any A, phi of AB maps to phi of A times 0, which is 0. So this is just, this is the reason for the definition. You know, the guys who first wrote out the definition of an ideal, you know, were working in some, you know, eventually came to the conclusion this is the only possible definition that makes sense. Right? And moreover, if A is a ring and I an ideal, then there exists a ring A mod I and a homomorphism and a surjective homomorphism. So A goes to A bar. Taking A into A bar, so that, so if I call this, you know, phi or something. such that I is phi to the minus 1 of 0. It's the kernel of phi. Okay, so in this case, for example, I decide I'm going to take all the multiples of 6 to be 0. I do z mod 6, I get this ring that everybody knows called z mod 6, and he has the property that if I do z mapped to z mod 6, the guys that go to 0 are exactly the elements that are in the ideal. Right? So so you can think of this definition as being, as being a quotient by an equivalence relation. So the A bar is all the elements that are equivalent to A modulo I. Or it's a coset, if you like algebra. If you're a committed algebraist, then you probably think of this as a coset. Okay, so I need probably one or two more things about ideals. I need a notation for the ideal generated by some elements. So if I've got f1 up to fn in A, I write open brackets f1 up to fn, close brackets for the ideal of A generated by f1 up to fn. Right, and so what does this mean? This means, you can say it in some different ways, but it means, so f1 up to fn. I can also write this, if I want to, as sum of A times fi. Right, contained in A. So this is the inside A. I take all those elements. So this is the set of all elements, sum AI fi, such that the fi are the given guys, given elements, and AI in A, any. Okay, so in rings that are not, the trivial cases, in rings that are not, not something like Z or polynomial ring in one variable, it will often happen that my ideals need many generators, several generators. Okay, so this is just notation. This is just, or if you like, it's a definition of the ideal generated by some elements fi. So, if I have an ideal and it contains the fi's, then it certainly contains all of these just by definition of an ideal. So this is the smallest ideal containing the fi's. Okay, so any problems with this? I hope that everybody has seen these definitions. I hope if you haven't, then you probably need to do some homework. Okay, so there's this topic. I'm going to talk about Noetherian rings. So we know that Z is a principal ideal domain. So principal ideal domain. So that's a statement I made over there, that every ideal is either 0 or it's generated by a single element. Right, principal ideal domain. Every ideal is a principal ideal. Right, and the same thing for K of X is a principal ideal domain. Right, and we also know that PID implies UFD. Useful fact. So we saw this I discussed this quite a lot early in the course when I was talking about functions on P1. Right? So it often happens in commutative algebra. In commutative algebra, there's a popular type of argument that says A has some good property implies A of x has some good property, has the same property. Right. So I'm going to do this for Noetherian rings in just a minute. But you know, there's this. So you know, for example, if we're talking about for integral domain. So A is an integral domain, implies A of x, again, is also integral domain. Right. So for A UFD implies also A of x a UFD. So this will be this is sort of basically question 1 on the example sheet. I'm not going to say too much about it, right? There'll be some hints on the example sheet for how to do this, right? But you can ask the same question about PID. Is it true that A is a principal ideal domain implies A of x is a principal ideal domain? And the answer is, of course, no. But no for PID. But obviously, because Z is a PID, but Z of x contains ideals like, you know, P comma x. So the ideal generated by the two elements, P a prime number, for example, 2 and x, and you know, you can't find any fewer generators there. It's not true that that there's anything that divides both P and x. So K of x, x a polynomial ring over a field, is a PID. So that's the thing I discussed about 2 weeks ago. But if I take K of xy, then, you know, I can find an ideal in there, for example, you know, the ideal x comma y, or the ideal f of x and f of xy. F of xy, g of xy. Right? So you know, if I'm thinking here f and g, the picture I've already drawn before, f of xy equals 0, and g of xy equals 0. Right? And you know, this ideal is something to do with this finite set of intersection points. And you know, you can't hope to generate this ideal here by any one element. You need these two elements, or you need something very similar to these two elements in order to be able to generate the ideal. Right? If you take xy, you know, this ideal xy, this is all functions that vanish at 0. Right? So if I've got a function that vanishes at 0, then, you know, I write it out as a polynomial. It's got, you know, maybe I take some f is sum of aij x to the I, y to the j, and then I ask, is it true that f is 0 at the origin? That just means that the term a00, the constant term in the polynomial, is 0. And if that happens, then f is obviously a multiple of x plus a multiple of y. But you certainly can't expect it to be a multiple of just one of them. Right? So these statements are completely ridiculous. It's completely stupid to expect to be able to play this game in this case. So this shows already that you know, these questions, for example, of divisibility. When is it true that some polynomial divides some other polynomial? And this question here of inclusion of ideals are just not the same question if you're in these more complicated situations. Okay, so I'm going to talk about this thing called Hilbert's so definition of a Noetherian ring. And then later on there's going to be this thing called Hilbert's Hilbert basis theorem. So so this principal ideal condition is the condition that every ideal is generated by just one element, right? And so this condition here is equivalent conditions. So 1, every ideal I in A is finitely generated. Right, so finitely generated means like this. It means there are some finite number of elements, f1 up to fn in A, so that the ideal is the ideal generated by those elements. Right, and I'm just saying the same thing in several different ways. This is called the ascending chain condition. So any chain, every chain I1 in I2 in and so on in in plus 1. So if I have a chain of ideals, each containing the other, each containing the one before, every such chain must terminate. Right? In other words, there exists an n0 such that I of n0 equals I of n0 plus 1 equals I of n for all n greater than n0. Right, so I can take my ideals, I can make them a little bit bigger, a little bit bigger, a little bit bigger, and then this condition says that this must stop after some finite number of steps. So, you know, if you think about divisibility, in n, I take this element n, I try to write him as a product if possible. So if n is divisible, if n is not prime, then n is n1 times n2. And then I look at n1 and n2 and try to play the same game with them. And as we all know, if we're working in Z, this must stop. This happens so many times. You can take the n and divide him up so many times, and at the end of that, that's got to stop. So that's the kind of condition it is. And the third condition is sort of basically for logical tidiness. The third condition is every non-empty set of ideals, I sub lambda. So, you know, it's a set. So it's indexed by some indexing set. So you know, the idea is I don't want to write 1 up to n because this is possibly infinite. Has a maximal element. So basically this is the same thing as the ascending chain condition. If in an ascending chain condition I have this potentially infinite number of ideals, and one of them must be maximal among all of these. So in other words, i.e. there exists what do I mean by maximal element in the set? There exists lambda naught such that I lambda naught is not contained strictly. So this doesn't happen, I lambda. Right? I get to a certain point where I can't get any bigger and stay within the set. I'm making this more complicated than it need be. Let's leave it at this. Okay, so let's just discuss these because these are useful in different ways. So let's do 1 implies 2. So given I1 in I2 in in plus 1, right? Take I infinity to be the union of all the I equals 0 up to infinity. Right? It's just that they're all included one in another, so let's just take the union of all of them. That's a forward inclusion. This is still an ideal. It's still an ideal because I take two elements in this union, then they've got to be at some stage, and then I can do my whatever it is I have to check. I can check it at this IN. Okay, this is still an ideal. And so if this I infinity is f1 up to fn, I'm assuming 1. I'm assuming that every ideal is generated by finitely many elements. Then if this union is f1 up to fn, then each of the fi's, each fi belongs to some I, ni or something. And if I take n equals the max of the ni, then I'm home. Then I infinity equals I sub n. Right? So, the important thing here is there are only finitely many elements here. And so, I go up this chain. At some point I add in f1, at some point I add in f2, and so on. There are only finitely many elements. Each one of them has to get added in at some point, and then the chain stops growing at that point. So 2 implies 3 is purely logical, and it uses the axiom of choice. So I'm sorry about this, but that's just the way it is. When I was an undergraduate, the algebraists were very, very keen on telling us which things use the axiom of choice. People who do set theory or logic don't care about the axiom of choice. It's an old story for them. But people who do algebra seem particularly keen on it. So I'm not going to discuss it in detail. The idea is, suppose I've got a non-empty set of ideals, and suppose that it doesn't have a maximal element. That means that every time I've got one of these guys, I can find a strictly bigger one. Right? And so I take a strictly bigger one, and then a strictly bigger one, and then a strictly bigger one, and I contradict 2. So if I lambda is a set of ideals, and for every lambda there exists lambda primed with I lambda contained and not equal to I lambda primed, then I start I1 equals any I lambda, I2 equals that I lambda primed, as in this assumption, and then I continue like this, and In plus 1 is I lambda n prime, and so on, is strictly bigger. Is strictly bigger than In. Right, and so that contradicts 2. It contradicts 2. Right. The problem with this argument is a logical problem that I said here I can make a choice, and that's fine. Given this axiom here implies that given this guy, I can find a strictly bigger guy. But the axiom of choice says, well, you can't necessarily make an infinite number of choices all at the same time. So I don't want to get into this. It's a tacky piece of algebra. It's a nasty piece of algebra, and I don't really. So if you do, if you're a professional in algebra, if you're a professional in algebra, then you know how to get around this. There's, you say Zornslemma instead of the axiom of choice. You write out some set and so on. It's really easy stuff. But most of us are not concerned with logic or with set, the finer points of set theory. And so this kind of argument's good enough for most of us. Okay, so this condition here, this maximum condition, is really very, very convenient. We're going to use it in several times. We're going to use it in several different contexts, and it is really very powerful. So algebraists like to use this. So proof 3 implies 1. So suppose that what do I want to say? Suppose that I in A is an ideal. Consider the set, so I lambda in lambda, consisting of all finitely generated ideals I lambda contained in I. Okay, so I is some subset of a ring A. If it's not empty, then I can find some elements in it. So I put in a few elements, and having put in f1 up to fn, I get the ideal. So I lambda is f1 up to fn for the first n elements fi in I choose. Right? So I just start off finding some elements in there, and so this makes finitely generated. This makes an ideal which is contained in I, and which is finitely generated. So this is certainly a non-empty set. I could take the FIs to be 0, for example. Right? So this contains a maximal. By assuming 3, this contains a maximal ideal. Say J. Right, so J is one of my set there, so he's finitely generated. So J is finitely generated. So if J is not equal to I, then choose choose G in I less than J, choose G in I not in J, and then consider J and G. Right? So this contradicts 3. This contradicts that J is maximum. This contradicts J is maximal. Right? So, you know, the point is just that this statement 3, every non-empty subset contains a maximal element. This is just a very powerful way of arguing, because I can always I can always start my argument, right, and then say, well, let's suppose that I get to the maximal element J. Then, if J is not actually the whole of I, then we have a contradiction, right? Because on the one hand, this J is finitely generated. If it's not the whole of I can put in one more element, and if that G is not in J, then this is strictly bigger, right? And so you know, this is the argument is really very trivial. We're just doing logical manipulations and so on. But you know, it's important. It'll be important to us to have these 3 different statements, 3 different equivalent statements. So, you know, example, whenever you give a definition, you should always try to have a counter example in mind. So maybe you don't know any examples. So let me take this. Suppose I take K of xy. Okay, so this is a model of a Noetherian ring. Let me write this as a K vector space. So I'm going to write 1 x squared, x cubed, and so on, and then y, and then xy, x squared y, and so on. Right. So this is has a K vector space basis like this. So what do I want with this? So take the subring. I want to take the subring K of xy. So here's K of xy. I want to take A to be the subring A, where A contains all monomials x to the so it contains 1, and it contains all the monomials x to the power of I, y to the power of j, with I greater than 1. Right? So in other words, I say, right, you can have anything you like, you can take any of these monomials you like, but you're just not allowed to take those. Yes? So in other words, I'm going to write down any polynomial like this, f of x, y, and so this is going to be sum of, well, you know, there's a constant term in there, a naught, and then there's plus sum of, you know, bij, x to the I, y to the j, and I'm only putting these in when I is greater than 0. Right, so you're not allowed here to write down y or y squared or y cubed or y to the 4th. So why is this a counterexample? So then I is the ideal generated by, what do I want? X, xy, xy squared, no, xy cubed is not finitely generated. Okay, is this, let me argue this because it sort of looks implausible. So I've written down x, and then I've written down something which is obviously a multiple of x, and then something which is obviously a multiple of that, and then obviously a multiple of that. Right? And the problem is that, xy is not a multiple of x in this ring. Right? Because you're not allowed y there. Okay, so let's just think about this. So A is this ring where I'm allowed to write down any polynomial as long as he doesn't have, in other words, the term y, y squared, y cubed, y to the n, and so on, are not allowed. So I write down, the thing I'm writing down here is the set of all polynomials with a naught 0. So this looks like the maximal ideal. A intersect with xy in k of xy. Right? So this is all polynomials in A with a naught equals 0. So in there I certainly have these elements. X is certainly in this, is certainly of this form, certainly in this maximal ideal. And then xy is also in this ideal, xy squared and so on. And, there's just no way of writing this ring. There's no way of writing this polynomial as a sum of only finitely many of those terms. Right? So this is sort of counterintuitive. You've only seen sensible rings. This is a kind of pathological construction. But so this is an example of infinitely generated ring. So the statement I want to get at is this, that A is an Noetherian ring implies polynomial ring A of x is also Noetherian. So the idea is, what do I want to say? A satisfies this condition 2, this ascending chain condition, and we prove that A of x satisfies 1. So this argument is called, this theorem is called the Hilbert basis theorem. So it was, Hilbert proved this around 1885. And then Emmy Noether, I'm sure many of you are aware of Emmy Noether as a sort of champion of women mathematicians. from around 1920, Noether developed this idea of Noetherian rings and used it in many different contexts. So Noether died around around 1935 in America, and the rings were named after her then.